Hi, I am so sorry. I know I promised that I would have this up on Wednesday, and I do not. I did not. I am really having a hard time processing the way this school year is ending, as I'm sure all of you are. And I really went into a terrible funk. But I'm kind of out. And I also realized that Blend is shutting down within the next week and a half. So I need to make sure that I set things up so that you have access to this over the summer, because most of you are still taking AP exams. And I know that realistically you're not going to have much time for this. So there we go. There's the foundation of today, the spirit within which we enter this space. Haha, I never use words like that, so it's so hokey. Anyway, we're going to talk about the area bounded by a polar curve, and it's a pretty simple concept. Basically, what you've got going on here is you're slicing this sucker up here, into little slices of a pizza pie, basically, and it's a misshapen pizza. And we're treating it like little tiny bits of a pizza. So each little tiny slice here, oh, I'm a terrible colorer, but you get the idea. I can't color within the lines, can I? Each little tiny bit there is a slice of pizza, and we're finding the area of each slice and adding them all up. So rather than rectangles, we've got pizza pieces. And that sounds really easy in theory. The problem becomes the graphing part. So the actual underlying foundation here is pretty simple. You're just adding up all of these areas of a sector, defining that as f of theta. Area of a sector, area of a whole circle, defining r as f of theta, and then we're the little trying to figure out how to draw this appropriately. The little width of each of these is here. Let me see if I can use it. The little width. Ooh, that's terrible. See? The little width is delta theta. Oh, these are really bad. That's terrible too. I'm sorry, I don't usually make you listen to all this. Okay, so we're multiplying our radius times our widths, just like we always were. And the area of a sector is always theta over 2 pi times pi r squared, where those pi's are going to cancel. So you're left with 1/2 r squared theta. So hopefully that makes sense to you. That should bring up some vague memories from geometry. Not that it does, it just should. Okay. Let me see. So let me see if I can highlight what we're using this where r is f of theta, and again delta theta is the width of each sector. I am so sorry that was so non sequitur and all over the map. The videos, it's my understanding that the videos from AP Calculus are currently down. They are supposed to stay up through May 31st, no longer. Once they're down, I am planning on making redoing those videos for you, because I am concerned about you going into Calc 3 or even Calc 2 without some foundation. Okay. So the previous page stated that we've got these little pizza slices that we're adding up, and our area is the Riemann sum, or the sum of all of those little pizza slices added up, which of course leads us to the Riemann sum, which the Riemann sum, ooh, sorry, oh, why is it doing that? This Riemann sum, I'm trying to keep it from going back page. This Riemann sum, which is the definition of that integral. So all of this is, if you know the formula, you're fine, right? It shouldn't be that stressful to you. It might be a little bit foreign, but the next bit is where people start having problems. And the next bit has to do with your calculator. And it really overwhelms a lot of people. Okay. So you are asked to sketch the graph of 2 plus 2 sine theta and find the area bounded by the graph. So what happens is a lot of people think they're in polar and think they're graphing appropriately, but clearly get a rectangular graph. And you know you've done something wrong. Or you have a less than optimal graphing utility, and you end up with something that doesn't look anything like what it should. What you want is either a cardioid or a lemmason. And I would imagine that in Calc 2 and Calc 3, you would need to know the difference. Okay, so here are some of the distinctions that you're going to go into college where these distinctions may have been underemphasized in pre-calc. They have been in years past. That doesn't mean they were your year. Equations of the form r equals a plus b sine theta, are all of those. Those will produce lemmasons. A cardioid is a certain type of lemmason, and I actually don't know if I'm saying lemmason correctly. Just pretend I am if I'm not. There are all different types of lemmasons. There's one with an inner loop. They look like kind of like ovals. When A is less than B, it's got this little inner loop like this. Ooh, that's the wrong tool. Like this, right? Then the dimpled lemmason doesn't look quite like that. Let me see if I can draw it. It kind of looks like a little tiny kidney bean, lima bean. That's a better descriptor. The convex lemmasons, they look kind of like flat ovals. They're really weird. Then the cardioid, that is what we have in front of us. And the cardioid is where we start today. So, the hard part about finding the area bounded by the graph is figuring out where the graph starts and where the graph ends. In order to figure out where the graph starts and where the graph ends, you need to know how to use either your graphing calculator or Desmos. And when you're doing this, I would recommend using both. If you have a TI-84 and one of the more current versions, out in the left-hand column of the graphing utility, which I left all of mine at school, you have tools that look like, I think one looks like that. You want to use one of those tools that will slowly, and I'm going to go down to the real graph down here, the red one, and it will take you from the beginning to the end of the graph. And that is going to be very crucial so that you can figure out the area. If you use the wrong endpoints, you're going to gum the whole thing up and you're going to be so lost. So, there we go, starting this problem by figuring out where the end and the beginning is. Okay, when you attempt the assignments that are in front of you, you're going to see that the hardest part is going to be figuring out the bounds of the integral. I am speaking about this little alpha and beta. I have highlighted in, or not highlighted, but boxed in blue, the place where I see the pattern repeating. If you look at it, they're the same numbers over and over again, but you've got to be really careful and make sure that you see that pattern repeat. Once you start seeing that pattern repeat, you can identify where your alpha and your beta are. And I swear to you, every year people have issues with this. Even Mackenzie Smith and Jacob Hartzer had issues with this. I know they're 5 years older than you, but both of them majored in engineering. So I feel like if they had issues with it, everybody has issues with it. So figuring out those bounds, really, really rough. Once you figure out the bounds, then the easy part is putting it into your calculator. In order to create this particular, this particular table, that's the word I'm looking for. I used increments of pi over 12. So in your table, that would be your delta x or your delta theta, depending on how your calculator is set up. So with that information, I can use the information on Desmos, and I know that this is 0 degrees down here, going all the way up to pi over 2, and all the way back down to 2 pi. It won't always be this straightforward. So that's how you graph it. Then you're just going to pop that little stinker into your calculator and integrate it. I'd like you to notice that it turns out the graph on the actual paper is not scaled the same as the graph on Desmos. I'd also like you to notice that I am still using the approximate symbols. It is not mathematically correct to say that the integral and that particular number rounded to 3 decimal places is equal. It is not mathematically appropriate. Okay, so it took me forever to draw this, not do the math, the drawing. Okay, so I chose to break my theta up into increments of pi over 36 because we're taking the sine of 3 theta, and 3 theta is the equivalent, how do I explain this? So if it was just theta, we would break it up into pi over 12, but since it's 3 theta, instead of 12, we can use 36, because 12 times 3 is 36. Yeah, this is clear as mud, isn't it? If you need clarification on that, feel free to set up a Zoom meeting anytime this summer. I'll try to explain it to you face to face. Oh, and I wrote this wrong here. Other than that, figuring out that theta, once you've done that, it's really easy to pop out the numbers. But I always have kiddos who want to make don't know how I did that. this down here your petal, but there are often major issues with making that your petal because that's in more than one quadrant. You want to pick a petal where it's in only one quadrant. So it would have been wise to either pick the petal that's displayed, or again, gosh darn it, not this one, but this one over here. I drew that wrong. Oh, yeah, that's right. Okay. So this one over here would have been okay. This one right here is okay. Either one for your start and your finish. Okay, done. Haha, tried to trick you. No, you need to use your formula, silly children. So we go ahead and set it up, and that's all we need to do is to go from 0 to pi over 3. And P.S. I could see that my pattern repeated on my calculator. I just didn't bother to write it down or talk about it. Lastly, we need to find the area of one petal of r equals 4 cosine 2 theta, and do not evaluate. Our delta theta there, instead of being pi over 12, will be pi over 24. I hope if that confused you on the last one, maybe that'll clarify it a little bit. Immediately you see when you graph it that there are 4 petals. But when you look at the table, you see that at 0, the value of your radius is 4. Well, you cannot start, I suppose you could, but you probably shouldn't start there because you're not really finding the area of a petal. You need to start at that center there. So wherever your radius is 0. So you need to look through your table. And again, this is where people have issues, is figuring out where to start and stop. So if you look, you are stuck in a dilemma on your calculator into going into negative radians over here, or going into positive radians but negative theta values. Hopefully you find negative theta values easier, because that is what I am going to do. I do not recommend doing the negative radii. I think that you would probably get super confused trying to graph a negative radii. I think that was hard enough in pre-cal without doing it right now. And just in case you were completely lost by what I just said, I highly recommend you get out your calculator. You should be doing this along with me and pushing pause. Okay, it just occurred to me that I have not been clear about why I'm writing down the entire table. I am not writing down the entire table to be able to graph it. I am writing down the entire table to figure out what my bounds are on my integral. So what I have just found here is this petal right here. Once I've found that petal and I've figured out where it begins and where it ends with respect to theta, I go ahead and put it in the formula. And right about now, you should be realizing that I misspoke earlier. I said that you don't want a petal in 2 different quadrants. You want a petal that has one full swoop, meaning no matter where you go within that petal, you can use, this is one continuous swoop. I believe some of the petals, particularly on this one, are comprised of 2 separate swoops. So this top part is an interval from like I don't know to I don't know. I'm just not gonna. And this part of this petal is an integral from I don't know to I don't know. I just don't want to calculate that out because I don't have to, and I don't want to waste your time. Okay, that is it for finding the area in polar curves for today. Take care. I miss you. Talk to you soon.